Roger. Copy. Gina very stable and no noticeable oscillations. Very good.
If there's a question that comes up, we might. Do you have chalk there?
Yeah, I do have chalk.
You don't have a name tag so we can tell who?
Yeah, we can move over. I know who I am, so
Oh, okay.
slip on.
Okay, why don't we start right off, and Captain Schirra will start with a resume of the mission, and then we'll go into Q&A right after that.
And before we do this, we got to get a slate in here for these sound boys. Roll them. Everybody up to speed?
Speed.
Liftoff.
That sounds like a DAP set.
This, I guess, will be one of the more casual press conferences we've had around this area. But to start off as casually as we can, we have a Saturday afternoon ahead of us, I gather. Not much has changed since we initially looked at the GTA-6 mission, other than the fact that we are trained to the point where we're aware of what the mission really represents. The rendezvous that is scheduled for this mission, of course, consists of the Gina launched on the Atlas from Pad 14 and the Gemini spacecraft 6 launched on a Titan II from Pad 19. If the Agena goes into a good orbit, one that we can handle with both Agena fuel and Gemini propulsion fuel, we will launch the Gemini one orbit behind the Agena. From that point, the Gemini flight is as others have been. We are placed into orbit, although this orbit will be described as a 87-146 nautical mile orbit, meaning 87 perigee and 146 apogee. From that point on, the ground range, or the Mission Control Center, will be plotting our trajectory and the Agena trajectory to modify our orbit from a relatively fast catch-up rate, in that we are initially elliptic, to ultimately a circular orbit, which will have an orbit of 146 miles as apogee and perigee. The burn that is made to put us in the circular orbit is called the NSR burn, or normal slow rate, meaning that we are behind the Agena, 15 miles lower than it, catching up only by the fact that the circular orbit, being lower, has a higher velocity. At a certain point, after we initiate this burn that puts us in this circular orbit, we are in the rendezvous mode. And at that point, from nominal time, it's approximately 60 to 65 minutes, we make the transfer burn. This timing is very critical and is determined by 3 ways in order of best accuracy. The first way to time when we make the transfer burn is by the angular measurement measured between the Agena and the spacecraft. The next technique, in case we lose parts of our total system, is to use range, and the third is time from the circularization burn. That is a burn that represents normally about 32 feet per second. This starts us then on a transfer similar to a Holman transfer. It's about as close as we can get to a Holman within the efficiency of the total systems. A Holman is the purest, cheapest transfer you can make. We will end up finally coming up below the Agena and ahead of it, much like the maneuver that we describe in aviation as an Immelman. We will have our heads down and will be just about approaching the top of a loop, still slightly pitched up. At that point, approximately 3,000 feet out from the Agena, we will effect what is called the braking maneuver, retarding our closing velocity from approximately 40 to 45 feet per second down to about 5 feet per second. This braking maneuver takes about our range decreases from approximately 3,000 feet when we initiate it to approximately 1,800 to 2,000 feet, the time required to make the burn. From then on, we are tracking line of sight on the Agena and slowly come into position, ideally about 50 to 60 feet from the Agena. Then we are continually slowing down, obviously not by much. 5 feet per second isn't exactly a speedy course. We'll slow down to about a half a foot per second to dock. This terminal phase, as I described it from braking, will be conducted during the daylight phase of one of the orbits. After docking, we will have had a good check on the Agena, both by the display panel on the Agena target docking adapter and, of course, from further information from the ground through its telemetry to the ground stations. We will then rigidize. This is done automatically by the function of making up 3 latches on the target docking adapter. Then we will be one spacecraft, Agena and Gemini. At this point, we will run various engineering tests to compare the 2 vehicles. As you can imagine, there are 2 stabilization platforms to see how closely they correspond. Make attitude changes while docked with the Agena, both with the Agena making the maneuver and with the spacecraft making the maneuver. There are some experiments that we will perform after leaving the Agena. One of them is a DoD experiment called D2. This will require backing away from the Agena. We will back away approximately 60 feet, and we will fly basically a circle around the Agena with a radius of about 60 to 100 feet, taking stills and movies of the Agena through the varied backgrounds as we go up over the Agena, pitching over and coming down, doing a loop in essence around the Agena in plane, always pointing our nose at the Agena. After this particular maneuver, we will have another day dock, and Tom Stafford in the right seat will effect the second day dock. After that, we will have 2 more separations in the night side and do a night dock from each seat. We have an attitude control stick, of course, in the center, which either man can use, and a maneuver controller on either outboard side of the spacecraft for respectively the right and left seats. That, in essence, is the mission. We will ultimately back away from the Agena, and at a known velocity, we'll be tracking the Agena with a sextant to measure angles between known stars and the Agena. This is to get some data for the Apollo technique for Rendezvous using an optical star tracking system. The sextant would be considered then in that category as a backup device. This is to determine our capability to measure these angles as compared to other experiments, particularly one on GT4, where this same angular technique was applied, measuring the angle between 2 known stars and a known star on the horizon. Offhand, I can't think of any other major things that we haven't discussed as thoroughly as we have in the past. If there are any questions, I think that might be appropriate, or maybe some of the other fellows might have something they want to say. Gus?
Oh, I think you've covered it pretty well.
Well, there's not much to add to the basic mission except what Waller's already covered.
What can I say?
Let's throw it open to questions and answers. Since the networks and the wires are going to have some additional time, let's not have any questions from them at this time, please. Let's get the questions from the people that aren't going to have any additional time.
Wally, I understood you to say that you were going to maneuver both with the Gemini and with the Agena. Does that tell me you're going to light up the Agena engine?
At this point in time, there are no plans to light either the SPS, which is the secondary propulsion system, or the primary propulsion system. What I was referring to were the fact, or is the fact, that we have an attitude control system on the Agena which can maneuver the Agena in attitude to any cardinal point. For example, we would use the Agena to yaw the complete spacecraft, meaning Agena and Gemini, when docked, 90 degrees. Then we would use the spacecraft to yaw the total system back 90 degrees to check the motions of both vehicles when docked and rigidized, of course.
You said at this time. Do you have the capability for burning that engine?
We do, yes. All propulsion systems.
Wally? According to the information that we've picked up around here, there are 2 SPS burns under consideration. One of them would drop the whole outfit from your insertion orbit or your final docking orbit to a 146-161, and a second burn dropping it to a 146 circular. Have these been thrown out completely, or are they still being considered?
None of these things have been completely finalized at this point. Those are valid concepts that have been looked at very carefully, have been integrated into proposed flight plans. Such things as a re-rendezvous have been considered, and none of these at this point in time have been finalized as the mission flight plan for this particular mission.
Well, as close as you're getting to the final or to liftoff at this point, how soon can we expect a final flight plan?
I'd like to have that answer myself. Now, it doesn't. These particular maneuvers do not affect our state of training. They merely add to the total package of the mission. Our training must be focused naturally on the ascent mode to get into orbit. For example, this morning I was working in the launch abort trainer that we have here, and all this past week the 4 of us have been in St. Louis doing rendezvous in every mode that we can conceivably expect to see happen. We, at this point in time, have that nailed. The D2 experiment I described, where it's a precise tracking exercise, we just did yesterday in St. Louis. So these things are done. Now, if we add a burn to the mission, all it really means is it's another burn. It's not a classical training maneuver. Most of the burns basically affect the readiness and overall training of the ground network rather than the flight crew.
Does the spacecraft have the capability of making these orbital changes, or would that require the SPS?
No, we can make quite a large orbital change with the onboard system. Naturally, we start out with an 87-146 and end up with a 160-161, which the spacecraft is doing on its own. So in turn, we can obviously bring it back down to the equivalent numbers.
But that would be the spacecraft minus the Agena.
If we drag the Agena along with us, this would be a little more work for the spacecraft, yeah.
What is likely to be the more difficult, the docking or the orbiting of the Agena?
Well, the orbiting of the Agena we have to depend on, I guess, General Dynamics and Lockheed to accomplish, and then, of course, the ground network to put it there. Once it's there, then the die is cast, the Gemini can go. And that's why we at least want one orbit out of it before we lift the Gemini off. So assuming that that mark is made, then the rest of it is merely putting the Gemini in the right place. For a flight crew answer, I guess probably the most difficult part is the terminal phase, getting right up to the Agena in position to dock. We unfortunately can't put all of these things in one place to simulate. We can simulate down to about 60 feet with the devices we've been working with. Then we can leap on the docking trainer, which I think most of you all have seen, and go in from there. And that phase out doesn't seem to be difficult at all.
At what point do you no longer have navigational aid from the ground? Where are you on your own?
We're on our own from the circularization burn. We then are more accurate than the ground. This is the burn where we go into the 146 circular orbit. So it's really a twofold operation. We're depending on the ground to get to that point, and the ground is depending on us to get from there to dock.
Wally, Gordon Cooper and Pete Conrad, before their mission, were just a little bit concerned about how much time they had to train and getting all the things done before the mission that they felt were appropriate. the letter said they got it all done. How do you feel at this point? Have you got time to do all of the things you feel you need to do?
I guess the answer to that is you never do have enough time, but we are not as hardly pressed. At the time Gordon was feeling these pains, we too were, and part of our solution to this was an engineering simulator at McDonnell. In essence, it has worked as a third Gemini mission simulator in that it's a part task trainer for Rendezvous. And we had only 2 Gemini mission simulators contracted, built, and available for us, one at the Cape and one here in Houston. And these were much more complicated to get prepared for Rendezvous training. As a result, with the utilization of this third simulator, we've had a real good leg up on it. In fact, I guess we could say we hadn't had much out of the 2 mission simulators at this point.
Well, I think you should also add that remember, Cooper and Conrad were an Apollo program primarily before they got assigned to this flight. And after all, this group here has worked with GT3 for a long time, so we've had quite a bit of simulator training and as far as retrofires, launches, reentries, this sort of thing is concerned, so we're way ahead of the other crews.
So you feel like your combined work with both
Of course.
your flight and Gordo's flight.
That's a very big point, Gus. The only new thing to us was the Rendezvous, so we had to go scrabbling to find a device for that.
I don't want to monopolize, but with all of this maneuvering and everything, there's been a lot of talk about the food and the work-sleep cycles and this sort of thing. Have you all firmed up any plan on the work-sleep cycle and the eating business?
Yeah, basically what Gordo said, we'll be working together, eating together, and sleeping together.
True togetherness.
Yeah.
Simultaneously or together?
I think the proper choice of words is simultaneously.
Wally, after the braking maneuver, just how hard is it to do the docking? Is it easy to come in too fast?
No, we have very good control of the system if everything is working well. We have plenty of control authority. We have a varied selection of control modes. The only difficult thing that we can imagine is not seeing the Agena change size, and this would be strange, in that we start braking at 3,000 feet, and that is a fairly large object at that range. It's not farther out. So we are dependent on radar until we really see the Agena as far as judging range. If we have radar, it's quite simple.
In doing it, is it like flying formation in an airplane, pulling up into position like tail end Charlie?
Unfortunately, it's not. We initially thought it was, but there are too many degrees of motion to handle, plus orbital mechanics. And you don't just point at it and decelerate and expect to keep sliding right on in. You may, for example, be going a little bit too fast and go over it, where with an airplane you can push a stick forward and you'll still come to the airplane you're trying to join up on. You can throw out the speed brakes and decelerate, or turn slightly and ease away. But in orbital mechanics, you can go roaring off into a quadrant, as we call it, from which it's very difficult to re-rendezvous.
Did it take a lot of training then to smooth out the maneuver?
That and using everything we had available. It's putting all the cues together in one package.
How much maneuvering, how much fuel are you allowing for maneuvering? Have you determined that yet?
We start out with quite a load of fuel in contrast to the previous flights. It's roughly 700 pounds. I think it's 690 something. And from this, we will use some of the fuel for the separation burn from the Titan booster when we're in orbit. That's only about 10 feet per second. You might reckon the fuel, by the way, it is almost equivalent to 1 pound equivalent to 1 foot per second. So we interchangeably will say feet per second for a maneuver or pounds. And we naturally read in the cockpit feet per second with the incremental velocity indicators, the IVIs that you all may recognize now. The IVIs read in all 3 navigation axes, fore, aft, up, down, left, and right. So we get every burn we make logged on this readout. Now, we have budgeted a portion of this fuel. We haven't really pinned down the exact number for correcting the out-of-plane that might develop between the spacecraft and the Agena. Initially, we talked in terms of 240 feet per second budgeted just for that, which is almost a third of the total load. We've learned more as we've done more trajectory analyses and feel we don't need to give that much away for that contingency. It's not necessarily that we would use the 240 feet per second. We found that we can, at least with simulation, from the NSR maneuver, affect docking with approximately 240 pounds. So we still have 240 left if you talked about all the things we'd use. So we're not really hard up for fuel. We probably have quite a cushion. At least we hope we will.
I have two questions. How long is the mission in revolutions, and could we have a list of the experiments that you're carrying on board, please?
Well, first, I'll do the mission part, and I can hold my breath and let Tom do the experiment part. The art of rendezvous is quite complicated in that what we're doing is counting down 4 separate systems when you think about it. That's the Agena, the Atlas, and the Gemini, and the Titan. So they all have to fall together. Now, we will launch if we have a good Agena, but it may take a little bit longer than the nominal 4 orbits to get into rendezvous position. If it does, for example, if we use up our launch window, if we launch late by 1 minute and 40 seconds as an example, the whole profile is shifted 1 orbit. Well, our launch window can go up to about 25 to 30 minutes. Then we may delay and go up the next orbit. The window is then smaller. We may, for example, not be able to make it that first day and go up a day later or 2 days later, depending on when we cut off the Gemini. So all of these variables should be reckoned with. So we call the capability of the spacecraft 2 days, meaning that we have the power supplies, the consumables, electrical power, propulsion, food, and the men capable of lasting 2 days, obviously. Now, if we get everything done that we have scheduled, we may terminate the mission earlier. This would be sort of the real-time planning. So it's open-ended up to 2 days is the best way to describe the mission. Now, when we come down, of course, is determined again by the optimum recovery areas. So that in itself is a constraint. So that's what you play for. If, for example, we terminated the mission at the end of the first day, it would be 15 revolutions. We would come down in an area called 16-1, which would be in the Atlantic. Now that would be if everything was done that we intended to do on the mission and nothing left open. In other words, it was 100% complete. This could happen if we got off right on time and got right into position. Have some experiments.
On the basic experiments that we're carrying on the mission, the first one, we'll go right down the list, is the D1 experiment for the Department of Defense. This is a measurement of celestial objects through photography, and the primary body we're going to try to measure is the moon. Unfortunately, somewhat near our launch date, we're going to be near the new moon phase, so this may be rather difficult. However, I think we'll try to get photographs of several planets using this photography gear that we'll have on board. The second experiment is the D2 experiment, which is the photographic definition of nearby objects in space from various positions with lighting backgrounds, and this is what Wally described as the maneuver that we will do around the Agena. We'll basically do a 360-degree circle in plane around the Agena taking pictures. The D3 experiment is a mass determination experiment in space in which we will calibrate the thrusters on the Gemini by applying a known velocity over an increment of time, calibrate our thrust. We know what the mass of the Gemini is, and then we'll from there on continue the mass calculations of the combined bodies. We have the S5 and S6 experiments. These have been conducted both on GT4, 5, and 6. This is synoptic terrain photography and also the synoptic weather photography. Naturally, we'll have the areas over Mexico if we have time to work those in. This will have to be a real-time decision as to how it works in with the rendezvous. And no, the basic weather photography will just be targets of opportunity and the frontal systems and certain air mass systems that we'll have. And those basic ones are the ones that we carry on board the GTA-6.
Oh, there's D8 also.
Oh, right. There's D8, which is the radiometric experiment. We have fixed dosimeters in the spacecraft, and we'll have one movable and one fixed large dosimeter in the spacecraft, and we'll calibrate certain areas that have more than the nominal background radiation involved. This was conducted on GT4 also.
Wally, I actually got two questions here. How critical is your electrical power supply for this flight?
We have enough to run almost fully powered for one day. So obviously if we have a 2-day mission, we'll be in the so-called drifting and dreaming status, basically powering down to conserve electrical power and carrying a typical load of about 12 amps. This is due to the fact that we have a battery mission, of course. We have 3 batteries, which we talk about as being 400 ampere hour batteries, but if they're good, hot, fresh batteries, we might see 450. So there's a delta amperes, if you want to of 150, which is considerable. In other words, that would be something over 10 hours. So you play that one pretty close. Now, if we, for example, do launch late in the window and have to delay Rendezvous, say, until about the 14th or 15th orbit, we will be powered down for a considerable period of time prior to Rendezvous.
Okay, second question for Gus and John. In view of the trend of the backup crews moving ahead 3 flights and becoming prime crews, do you expect to get the prime on GT9, or are you looking toward a split up like they did on Ed and Jim, where they split the crew, and do you expect to be split up and maybe make a bid for Gemini 12?
Oh, I don't know how to answer that. I would certainly expect us to be split up. I think John is due for his own flight.
John, what do you have to say about it?
I hope Gus is right.
Related to that, Wally, I won't reveal your age, but it seems to me that you're creeping up here along with me. Are you still looking fondly at Apollo and the trip out to that there place?
Your old friend has helped no much. Do you feel your age? Very good. I think that's really a good answer. In fact, I guess I outrank you now, don't I, Shorty? No, I think that's a physical plateau that you have to face as time goes on, and I have yet to face the problem of age, so as long as I can meet the requirements for a mission, I intend to keep my hand in.
Gray-headed friend.
That's why I have this bald-headed co-pilot to make me look younger.
I'm only 34, Shorty.
One question, Wally. I wonder if you could give us an indication of changes or modifications or improvements or one thing or another that are now being applied to your spacecraft as a result of Gemini 5.
Turned out there were minor things that came out. There were some questions about the radar set later in the mission. This was a minor component. I believe it was a capacitor that had caused a glitch in the circuit. This is being reworked. Other than that, there were no major problems from 5 that did affect us. When Gordo called down a real-time message for me about putting a grease mark up in lieu of a reticle, we both knew it was a joke that I couldn't do without it. And his problem with the sunlight blasting him in the face with it is one I had reckoned with and hadn't, I guess, told him about my fix, which is a little rubber shield around the edge of it. Initially, I'd put it in to protect the mirror from hitting me with light due to a cabin light. So this would solve that problem. His reticle itself failed, I guess you all know, because of a short in one of the wires. Well, that kind of thing you just don't want to happen, but we do have an alternate power supply.
You're flying shirt sleeve, are you not?
No, we're not. We're flying suited.
You're flying suited.
Right.
How did the two of you get together? Did you know each other before you became astronauts?
I guess to answer that, simply no.
Did you have an option of picking your man, Wally?
Well, you can. I guess what we really say is we have right of first refusal.
Uh-huh.
You mentioned that you could launch in the second orbit of the Agena if you missed the first one. What will the difference be in launch windows?
Well, that's one that you really don't answer intuitively. This is wrung out of a whole bank of computers, and we have documents that are launch documents, launch trajectory documents that lay these out. And I, frankly, would defer that kind of accurate answer to you to get from some of the gang that work in the trajectory group under FOD, under Chris Kraft's group. Actually, Bill Tyndall would be a good source for answers like that. There have been some very careful studies made. It's approximately, I think it's another 50 minutes you can hold after we lose our first window.
One thing we plan to do on this mission is to have yaw steering on the second stage of the Titan, and we hope that the Titan will steer us right in the plane as close as we can get to the Agena plane. So it's hard to really say. It depends on the performance of the Titan and how good that can come out. You can't, I don't think anybody can answer that right now.
Okay, thank you.
A layman's question, what would happen if you couldn't separate?
Talk about zero lift.
The cheetah?
Doesn't make a lifting re-entry.
That dead black rock. No, the unstable.
Further up and
Yeah, that's,
almost
yeah, this explosive device in there. This is very,
back up in that.
Yeah, same technique exactly, except the computer should better have the right load in it. Huh? While I was sitting up here? I can start down the case.
this kind of mission? Well, the thing is so designed so every deal on board the vehicle is grounded.
Huh?
No, we have to have quite a bit of help on the ground.
Cut his throat.
You wanted to cut his throat, or you wanted
He wouldn't hold enough.
John knows some bad things in my background.
Oh, really?
Give up, Lou? Did you get it?
Houston. That's beautiful. This has got to be one of the most proud moments of my life, I guarantee you.